Assalamu alaikum. Welcome to the next class in electrical machines first. So, continuing with the previous classes in which we discussed about some basic topics in magnetic circuits. So, in the last section of the last class, we discussed about the BH curve and hysteresis loss. Today, we'll discuss about the eddy current losses. So, as we know, and when we have a varying nature of the flux that is linking some core or some magnetic material, it induces a voltage in it. And because the core is continuous, it will have the path for the current to flow. It results in circulating current in the core. So since current passes through the core has some resistance naturally. So when current passes through resistance, it reduces some power loss, it produces some power loss in the core, and that power loss is dissipated as heat. So these eddy current losses, or we can say these eddy current produces some losses which are undesirable for the transformer operation, or we can say some magnetic circuit operation. So let us say we have this type of the magnetic circuit. We have this current, this is the coil. So it produces a flux line like this. Let us see how this eddy currents will be produced. So this is the top view of the same core. This is point A, this is point B, just to make you clear that if this is the top we are looking at like this towards this core. So flux is coming up. Coming up means cross. Sorry, coming up means flux will be coming up. Usually there should be a dot over here. It is that's showing the flux, but let us say we have a cross that flux is going into this. When flux is going into this, actually I should have shown it this way, because when we have direction of flux shown like this, the flux will be coming up from here, it will be going down from here. When flux comes up from here, we usually show it by dot, and flux going down into the page, that's into the plane of page, we show it by the cross. So let us assume the other way around, that the direction of flux is like this, that it is going from A to D at this point, and it's coming from C to D from this point. That it here it will be cross, and here it will be dot. So when this is the case, the currents will be flowing in this case in such a way so that these currents will try to oppose the flux. That means this current will be, or this circulating current will try to flow in such a way so that it opposes the flow of flux. So it means it produces the flux in opposite to the flux of the actual winding. Since this flux is going from A to D, these currents will try to flow the flux in this winding from D to A, so that net flux will be reduced. When such is the case, that means the flux that is produced by the eddy currents will be coming upwards. When that is the case, so calculating the current direction, or that is to be done by pointing your right hand thumb towards the direction of the flux. Now direction of the flux will have to be upwards from D to A, that is the outward from the plane of the page, and the direction of your fingers will determine the direction of the current. That is what I have shown over here. The direction of the flux will be opposite to the direction of this, that is from A to D, sorry, from D to it should be from D to A, that is upwards. When the direction is upwards, you will see the direction of the flux, sorry, the direction of the eddy currents will be in this case, in this direction. That means it will be counterclockwise, because it will when the currents flow in this way, the flux will be out of plane of the page, which will be opposite to the flux, actual flux, which we have assumed in this direction from D to A, or we can say A B C D A, sorry, A D C B A. Similarly, for this case, since we are assuming that the flux is coming from C to D, it will be coming upwards. That is actually this flux is coming upwards, it will be a cross. When this is cross, so these currents will be these currents will flow in such a way so that they produce the flux opposite to this flux. Since this flux is going from C to B. This will be opposite to this, C to B, and this is the case. So it will produce the flux in the direction of B to C, that is downwards. So when it will produce the flux from B to C, so we have to point our thumb into the plane of the page, and you will see that the direction of our fingers, which will be clockwise, will be the direction of the eddy currents. You can see from here also, it is very obvious from here. This is the magnetic flux or magnetic field flux density, that is into the plane of this, into this core, and this current will be flowing in such a way so that it produces the flux in opposite direction. So when you keep this thumb in this direction and your right hand thumb in this direction, so you will see that the current, that is the fingers will be pointing in this direction, current will flow in this direction. So this right hand thumb rule is actually used to find the direction of the eddy currents. So here I just try to show you how this eddy current direction can be found out. So this is how eddy currents are flowing in consequence of the varying nature of the flux, and this eddy current flowing in the core will result in the power loss. So eddy current is also given by an empirical formula. So I have not derived here, this can be derived also. It is given by Ke, where Ke is a constant for eddy current loss calculations, F square and Bm square. This will be also given by watt per meter cube. It should be actually Q not square. So please try to correct it. Now this is an important formula, and we will be using this time and again, as I have told you the formula for the hysteresis loss. Where this Ke is the property of the material, it is given by Ke dash d square by this resistivity rho. D is the thickness of the lamination. Usually you will see that this core is not made of the solid one, it is made of the small thinner laminations. So these small thinner laminations actually are used to reduce these eddy current losses. You can see the direction of the eddy current losses like this. So it has to cross these lines, and these lines are very much insulated from each other. You will see their resistance will increase by a large amount. When this resistance increases by a large amount, so this EMF, that is induced EMF divided by this resistance, large resistance, this current will reduce. When this current reduces, automatically resistance loss will also reduce. So you can see from here, eddy current loss is dependent upon the thickness of this insulation. More the thickness, more will be the eddy current loss. Smaller the thickness, smaller will be the eddy current loss. So we need to keep this lamination as small as possible. You'll see, I will tell you in coming lectures what will be the thickness of this lamination. Rho is the property of the material, that is resistivity of the material core. More the resistivity, less will be the this eddy current loss. Frequency of the supply, F is the frequency of the supply, and D is the maximum value of the flux density that will be using in this code. So this is about the eddy current losses. Now how to reduce core or iron losses. Actually the combination of this eddy current loss and hysteresis losses are known as sometimes core losses and sometimes iron losses. So eddy current losses are reduced by using the laminations and high resistivity core. I have told you just now that thinner laminations can reduce the eddy current losses. And high resistivity core. The resistivity of the core is increased by using silicon steel, and 5% of silicon is added to the steel to increase its resistance. Beyond this, it actually makes the steel very brittle. So 5% is the optimum value. So it suffices the purpose of increased resistivity and lesser brittleness of the core. So usually pH is reduced or hysteresis loss is reduced by using the cold rolled grained oriented steel, that is CRGO steel. So actually it is, you don't have to go into the detail of this CRGO, just remember this is the CRGO steel. Actually it is, we can say, molecular level, on the basis of the molecular level, this steel is oriented in one way or other way, because you might have studied in 12th class, we have cubic cell, we have a face centered cell, we have other cell. On that means molecular way, or we can say cellular. When we go on the cellular dimensions, we need to roll it in cool temperature. so and orient the steel in a particular way. I will not go into that details, but for your general understanding, I just want you to just to remember it that for reduced hysteresis law we use the CRGOs or cold grain oriented steel. One good topic which is very important and sometimes it may be asked in interviews and some other exams, that is the magnetostriction. So this magnetostriction is actually found in the ferromagnetic material. When this material is magnetized, its dimensions change slightly. So the sample being magnetized either expands or it contracts. On magnetized, that in one cycle of magnetization, or we can say positive magnetization, it may increase. I mean, the negative cycle of the magnetization, it may decrease. But this elastic strain, this induced elastic strain, that is dl by L, that is what is known as magnetostriction, or we can say change in the dimension due to this magnetization. It is of the order of 10 to the power minus 6. That means 1 micrometer will be changed in 1 meter. So it is small, but it has a problem of it results in humming sound in magnetic materials. You might have seen or you might have observed a sound in the transformer that is very, you can say, which is not good. It produces the bad noise, which is not good for our ears. So we do not. We can say that this sound is not good for us. So that particular sound usually in inductors and transformers, that is because of this magnetostriction. Now we'll come to the main topic, that is the first topic of our subject, that is the transformers. So before going into the definition of the transformers, I will first define you what are the electrical machines. So electrical machine is a device in which an electromechanical energy conversion takes place. That means energy is changing from electrical to mechanical or mechanical to electrical. Any machine that is doing such change of the energy is known as electrical machines. For example, motor that changes the electrical energy to mechanical energy, or a generator that changes the mechanical energy to electrical energy. In such machines or in such equipments, there is an exchange of electromechanical energy. Such machines are known as electrical machines. For example, electrical motor, we have electrical energy changed to mechanical energy, of course through the magnetic medium. We cannot do anything without this. Similar generator, we change the mechanical energy into electrical energy again through the magnetic medium. So the examples for the electrical machines are DC machines. We may have DC motor or DC generator, induction machine motor or induction generator. Similarly, synchronous machine, we have synchronous motor or synchronous generator. All these machines we can say are the electrical machine. But transformer is not an electrical machine, and transformer is changing electrical energy again into electrical energy through magnetic coupling or through magnetic medium. There is no electromechanical energy conversion. That's why transformer is slightly treated as different from other machines. So it is a static device. There is no rotating part in transformer. In all these machines we have rotating parts. It is a static device that transfers electrical energy from one electrical circuit to another circuit through the medium of magnetic field, and there is no change in the frequency. That is what transformer means. This is the basic construction of this isolation transformer that we have. We have a number of turns on this side of the link. We have a number of turns on this side of the link. It has a number of turns of N2. It has a number of turns of N. And usually we connect supply on this side of the transformer, and we see what is the voltage level and the current level on this side of the transformer. The flux that is produced by this winding will be linking through this magnetic material to this winding, and because of this varying flux we may have some induced voltage over here. This can be measured, or this can be taken to this. The electric circuit which receives energy from the supply means it's called the primary winding, and the other electric circuit which delivers energy to the secondary winding, to the load, is known as secondary winding. You can see, since this receives the supply, this is known as primary winding, and this delivers this supply or energy to the load. This is known as secondary winding. This is the general terminology that we will be using continuously in this subject. So we may have different types of transformer. One is the step-up transformer. This is a type of transformer whose high voltage winding is on the secondary side, or whose output voltage is more than the input voltage. The number of turns on the secondary side is more than that of the primary side. You can see from here. So you can see here it has, let's say, 5 turns and 4 turns. But in case of high voltage transformer, step-up transformer, we have high voltage winding on this side, we have low voltage winding on this side, or we can say we have number of turns on this side more as compared to number of turns on this. That means M2 will be greater than N1. So output voltage will be greater than input voltage. So this is what this means. So this step-up transformer is generally used in generating stations to step up the voltage. So usually generating stations generate the voltage at 11 kV and then transmit it, step up it to 400 kV and transmit it. Or sometimes it may be generated at 33 kV, again it may be step up to 400 kV or 220 kV and then it is transmitted. This is the use of the step-up transformer. Step-down transformer whose high voltage winding is on the primary side and low voltage winding is on the secondary side, or the output voltage is less than that of input voltage determined by the turn threshold. Again, as I have not mentioned in the previous step-up transformer, that the voltage that is increased will depend upon this transformer ratio, that is N2 by N1. Similarly, for a step-down transformer, we have high voltage winding on this side, low voltage winding on this side. N1 will be greater than N2, and this voltage will be less than this voltage. And the relation between these voltage, you will see that will be determined by this N1 and N2. That is the transformer ratio. It is used in the transmission, sub-transmission, and in distribution. Apart from the, you can see, apart from this generation, always we will be using step-down transformer. So in transmission, we may have 400 by 220 kV, 220 by 132 kV. This is the sub-transmission. We have 132 by 33 or 33 by 11. And in distribution, we have 11 by 0.44 kV or 11 kV by 230 kV per phase. This is the line-to-line voltage. 230 is the phase voltage. So we may have another type of transformer that is known as 1-to-1 ratio transformer or isolation transformer. So if the primary if the primary voltage and the secondary voltage, or if the primary number of turns and the secondary number of turns are equal, then the transformer is known as isolation or 1-to-1 transformer. If the number of turns on this side and the number of turns on this side are equal, you will see that the voltage at this side will be same as this side. So such type of transformer is known as isolation transformer. So they are actually used to isolate electrically two parts, for example, power circuit and control circuit. For example, if we have a power circuit connected at this side, a control circuit at this side, you can see since there is no electrical connection, we have a magnetic connection. So electrically they are disconnected. So this is actually used for the purpose of protection. In that case, here transformer ratio, voltage increase, voltage decrease is not the purpose. Isolation is only the purpose, electrical isolation. Again, it is also used to block while permitting the flow of, it is also used to block DC. I have not forgot to mention DC word. It is used to block the DC while permitting the flow of AC. Because we know that if we apply a DC over here, since the rate of change of voltage is not there, there will be a constant flux over here, and constant flux linking this voltage will be having no effect, no induced voltage. There will be no DC voltage output over here, but AC voltage over here will be having some value because flux will be varying. That is why even if we apply a DC over here with a limited value of the magnitude, we may not have any value over here, but AC has the value. That is why we can see even if we introduce a DC at this point, we will not get its effect at the output of the transformer. The transformer size in electronic measurement and control circuit, transformer size may be as small that it weighs only a few tens of grams. You can see it may be of the order of uh, grams, 1 gram, 10 gram, 5 grams, 20 grams. And in high voltage transformer, that is power transformer, which is 50 MVA, 100 MVA, it may be of 100 of tons. It will be very huge mass. So use of transformer, as I have told you, mostly it is used as step up or step down transformer, an isolation transformer and to filter the DC, as I just mentioned it. And the third is, which is very important in the power electronic circuits or electronic circuit, it is used as impedance matching. What does this mean? Usually for maximum power transfer theorem, we know that this will receive the maximum power only when its value will be equal to the value of Rs. But you know that it is not in our hand to make this equal to this. This RL is the load and it may vary from the actual value of Rs. So to make it equal to Rs, we introduce the transformer in between, and you will see in the coming lectures this RL is reflected to this circuit as N1 by N2 into square RL. So we can say it will treat, or equivalent circuit of this RL when we remove this will be this. So in that case you will see that when we have to make it equal to this, we change the number of terms in such a way so that this Rs will be equal to this resistance. So in that case we change the number of terms in this way, that's N1 by N2 should be equal to Rs square root of Rs by RL. Then maximum power transfer will take place through this RL. So this impedance matching is actually used in electronic circuits because this maximum power transfer has actually some inherent drawbacks, that's why we are not actually using it in our power system. Now coming to the construction of a transformer, when we talk about the construction, it means we have to discuss about the different parts which actually combine to make the transformer. So there are actually various components that actually combine to make a transformer, but we will be only discussing those which actually makes the transformer, mainly makes the transformer. So there are other, you can say, accessories which are connected to the transformer. We will not discuss those. The first one is that's the transformer core. As I have told you, we have transformer winding, we have transformer oil, we have transformer winding insulation, and transformer tank. So these two we have a little bit discussed earlier, but I will discuss it in detail. So transformer core, as I have told you, it is made of CRGO and silicon steel, and you know CRGO is for to decrease the hysteresis loss and silicon steel is to decrease the eddy current losses. It is usually made of thin laminations of 0.35 mm thick. Sometimes it may be used as solid core for high frequency transformers, and I will told you that also why this is done for these high frequency transformers. The core usually provides magnetic link between the two windings, that is this core. The primary and secondary coils are wound on the core and are electrically insulated from each other and from the core. So this is actually the part of insulation. We have to insulate the winding as well as the windings, it's different terms from each other, and these windings from the core. Usually we have two types of core which are commonly used. One is the core type, another is the shell type. So I think I will stop here. We will continue to discuss this core type and shell type transformers in the next class. Thank you.